There are different types of chemical reaction in chemistry: the combination, decomposition, single displacement, double displacement, and combustion reaction. In this particular video, we'll cover the single displacement reaction. Let's look at this image here. In a single displacement reaction, you see this molecule here and an element. Well, this element kicks off that very front element, kicks it off, and then takes its place right in front of that blue one. As you can see on the right, it has done that. The yellow is now in front of the blue, and the pink one now is sort of left by itself. Another way to put this is a single displacement reaction is a chemical reaction in which one element is substituted for another element. Now, this is a circular model, but I like to show you an example of a single displacement reaction. So here is a single displacement reaction involving silver nitrate and zinc. As you can see, the silver nitrate is the compound I was referring to when it comes to the pink and the blue. If I were to put it as a reference with color coordination, the pink represents silver, the blue represents nitrate, and the zinc represents yellow. Now you can see zinc will replace the silver, as you can see over here. So you see the zinc is now the yellow portion has replaced it, and you see the silver by itself, and the nitrate is next to the zinc. Don't mind the twos and the little twos in the back over here. That you will figure out pretty soon. But what I want you to get an overview is that the single displacement reaction occurs where this singular element is going to replace the one that wasn't single, and now that one becomes single. What a poor life. Anyways, and then, so how do we go about this? You're going to go find out that whenever you're encountering a single displacement reaction problem, you're going to encounter just the left portion, just the reactant. Right now, the reactant is are silver nitrate and the zinc. Your job is to figure out the product. Well, you could see the product up here, but how did you know that? How do we get there? When you encounter a problem like this, you want to first of all show work by splitting all of the aqueouses into its charged format. Here's what I mean. Silver and nitrate in water, they're actually in split form. Aqueous means that they're in their split form. So here's my silver. And my nitrate. I will draw several of them. Now not only are they split apart, but you need to encounter that they have their own charges. Nitrate has a negative charge, we know. What about silver? Well, what charge does silver have? Well, where is that even on the element periodic table? In the periodic table, silver is here on number 47, and it's part of the transition metal. However, even though many of the transition metal tendency to have different charges, silver is one of those that do not have a variable charge. Zinc, cadmium, and silver. Those are the ones that do not have variable charges, and you need to have it memorized or just look in the reference sheet. So here is silver, and silver has a charge of +1. So let's go back. So we know that all of these silver has charge of +1. I'll just write plus. What about for zinc? Well, zinc is a solid, so normally they don't carry a charge. However, in this scenario, I do want you to write the charge if it were to have a charge. If zinc were to have a charge, they would carry a charge of +2. How did I know that? Let me go back to the periodic table. Zinc is located in the transition metal, and zinc is also one of those that do not carry a variable charge and has a charge of +2. Okay, so now what do? We have split all of them apart. Great. Now that we have split them all apart and assigned their charges, we're going to rejoin them together in this box over here. In this box over here, the zinc, the positive charged element, is going to attract the negative charged compound, which is the nitrate. Okay. And not only that, for every one zinc, there's positive 2 charge. So it's going to attract 2 nitrates. So zinc, for every one zinc, it's going to attract 2 nitrates. Okay. So when they rejoin together, when this forms into a compound, what's going to form is zinc. And there's 2 nitrates, so NO3, and you're going to parenthesize with a 2, encapsulating both NO3 and then parenthesize number 2. What about the charges? What happened? They disappear when you write in a combination like this. What about the silver? Silver also you just write it as it is without charge. So in the end, there won't be any charges left over. What happened to the charges? Well, there has been a transfer of transfer of electron one point to another, which we will discuss in a different chemistry class. But this transfer of electron causes the changes of the charges. It was positive, now it's neutral. Okay. Anyways, here, zinc, nitrate, and silver is what we write on in this portion. Zinc, nitrate, and silver. Okay, but what state do we put in? What do we put right here? Is it solid, liquid, gas, aqueous? The one that is by itself is always going to be solid. The one that is by itself. And it's a transition metal. Okay, it's going to be by itself, transition metal, it's going to be solid. The other one that has been recombined, that's going to be your aqueous. Okay, so hopefully that's simplified the single displacement reaction. We'll do more in a moment. But we are not done yet because this is not a balanced equation. Here I have 2 nitrate. Whereas over here, I only have 1 nitrate. So therefore, I'm going to add a coefficient number 2. Well, that coefficient number 2 applies that there's 2 silver, which means that I need to put 2 silver on the right-hand side. And 1 zinc and 1 zinc. So I'm done. So let's do a learning check related to single displacement reaction. Predict the products and write balanced molecular equation. Copper has an oxidation number of +2. So here's my silver nitrate and copper, and it's going to go through a single displacement reaction. Now, before I even try to solve to the right, we want to show work over here to see what each element might carry when it's positively or negatively charged. And it already shows you, it already tells you what the copper charge will be, which is +2. It says copper has an oxidation number of +2. So that's automatic. So I want you to go ahead and try this portion out, come back and check the key, and we'll move on from there together. And here's the key. Now we're going to rejoin the copper with the nitrate. So here's my copper. All right, copper here. And copper has a charge of +2, which means that it's going to attract 2 of the nitrates since they're both singular -1 charge. So to neutralize the entire compound, you need 2 nitrates, which means that it's going to form copper nitrate with 2 out in the parentheses. Silver will no longer have a charge and it will be just positive. So let me write that on the very right side. So copper nitrate plus silver. So you see that silver got kicked out, right? So the one that is by itself, single, would be the solid guy. The one that is together, this one is aqueous. So now after that, you're going to see if this equation is balanced, and it's not. There's 2 nitrate, but only 1 nitrate here. So I'm going to go ahead and write 2. Then I see that there's 2 silver, so I'm going to write 2 here. Very similar to the previous question. Let's try this one. Try this and come back and check the key. And here is the key. You might be wondering, how did you get iron 2? I mean, isn't there a possibility of iron 3? You're right. It's because if you look at over here, every 1 iron, there's 2 chlorines. So if there's every 1 iron, 2 chlorines, and chlorine is a -1 charge element, so I need 2 chlorine, that's total of -2, right? Chlorine 1. Total is -2. So therefore and there's only 1 iron, so the iron has to have +2 charge in order to neutralize with the chlorine. And that's how I knew the iron was +2. This is a balanced equation. All the coefficient is 1.